All right, guys, it's great to see all of you. I'm really, this is a turnout, like, this is like pre-COVID turnout. Ever since COVID, it's like I couldn't seem to get people coming, but this is really a lot of people. So I'm really glad to see all of you guys. I hope that your studying is going well. I'll just make a couple quick comments and then we're gonna spend most of the next 2 hours just practicing more problems again. And some of these problems will be the same as the ones I did the other day, but I'm also going to have a few little carrots of surprises to keep you on your toes a little bit. But before I get into that, just a couple of comments. First of all, I've not written the test yet. That's what everybody wants to know first. I always do that at the very last minute, and I just pray that the printer doesn't break down. And then the other thing is, it's getting to be like crunch time as far as this exam goes. If you have not tried a sample exam yet, or if you haven't had any time to sort of work on the stuff yourself, you should make sure you have some time to do that. Hi guys. We're in the overflow zone now. Oh my gosh. Wow. This is really something. It's one thing to kind of listen to me solve problems, and sometimes I can make it sound kind of easy sometimes. I hope that's what I'm trying to do. But it also can lead to like a false sense of comfort. You're like, oh yeah, I understood everything Dr. Hannon said. I must be like totally on top of things. But there is a difference, right, between that and then really doing it yourself. So if you need to like turn my voice off at some point and just like get focused just on your own studying, make sure that between now and tomorrow, whenever you're taking the test, make sure that you do save some time to really test how you're doing, right? In other words, get some of those other voices out of the way so you can hear yourself think about this stuff and make sure that you yourself are confident in your knowledge of this stuff. So that's actually really important, because I've seen it happen more than once where, I've had students who, they come to all my review sessions, they're always at my office hour, and they're super engaged in it. But at some point, they just were having me hold their hand a little too much. So I love to do that. So that's why I'm a professor. I love helping people learn this stuff. But I also realize at some point, everybody does need to kind of be able to do it for themselves too. So, but for the next 2 hours anyway, you're going to get to listen to my voice. I'm going to talk about a whole bunch of problems that I think will cover the material pretty well. I already went over the kind of the high level of what's in the resources folder, right? So you've got a couple of sample exams, you know what the test is covering, the group works, the homeworks, you kind of know all that stuff. So I won't go over all of that again. I'm just going to try to jump in on some problems here, and I will do some theoretical problems as well as some more computational problems. I'll try to give a nice blend of all of that. And it's kind of in a random order, to be honest with you. And actually, when I write my exams, I kind of do that too. It's not necessarily in order. It's just like whatever question comes into my head next is the one I write down next. But anyway, let's do one to get started here that I think might be, that reminds me. Don't forget, there is an extra credit quiz. It's due at midnight tonight. I've already graded the ones that came in yesterday, but at midnight, I'm gonna like start sending out all the feedback on that. Once you get the feedback, be sure to look at that feedback. If you did the extra credit quiz, you want to get something out of it by seeing where I may have seen some issues that you had. But anyway, I would recommend, if you haven't done that, that's certainly something to do before midnight. Okay. And by the way, I'm going to be here all evening after this review. I'm just going to go back over to the other room and just hang out, listen to music, and maybe write the test if I have time. We'll see. I don't know when that's going to ever happen. Anyway, so let's do some practice problems for our midterm number 2. Wow, I should have done this for the first exam too. I didn't realize people were going to actually come. So anyway, so here we go. Let's do this example. Number 1, let's find a basis for V equals the span of 1, comma, 4 plus x, comma, 4 plus x cubed, comma, 2x cubed minus 2x cubed minus 2x plus 5. So we'll just take this as an example that we can start with and play around with it a bit, okay? So this is one of those problems where we actually don't know how many basis vectors we are supposed to have. Okay, so if we're working with Rn, right? We know the dimension of that is, anybody? N, right? If we're working with Pn of R, we know that the dimension of that is n plus 1, very good, right? If I take, let's say, the n by n matrices, what was the dimension of that?
N squared.
N squared, right? And if the matrices are not square size, then let's say they're m by n, then the dimension here is m times n. We know these numbers. So if I'm asking you for a basis for one of these things, then you'll know how many vectors you should be giving, because the dimension is just the size of the basis. But if I just throw a random vector space at you that you've never seen before, like this one, then we may not know ahead of time what its dimension is supposed to be, right? You with me? So let me run an idea by you, and you tell me if this is a fair statement. These look like polynomials in P3 of R. We know that the dimension of that is 4, and they gave us 4 things, therefore it's a basis. These 4 things would be a basis. Would that be a good argument? And it's too simple. It's a little too easy, right? First of all, these vectors could be LD, right? They could be linearly dependent to begin with. Also, this vector space is not necessarily equal to P3 of R. Yes, these are polynomials that are in that universe, but their span might be actually much smaller than the whole P3 of R, right? This could actually be a smaller vector space than it looks like. Even though I gave you 1, 2, 3, 4 things here, right, doesn't mean that this is going to be 4-dimensional. I love that chart. And by the way, somebody wrote a really nice chart outside my office. I think that was Reed. Where you have, like, you know, K is less than the dimension of V, and then K is greater than the dimension of V. You guys remember when I did this? Right? And then K equals the dimension of V. And then K is the number of vectors that I give you. And you compare that with the dimension of V, and you decide whether it's, you know, is it Li? Is it spanning set? Is it both, or is it neither? By the way, almost every sample exam that I've ever shown you for this section has one of these problems on it. The more times you've seen it on my exam, practice exams, the more likely it must be something I really like as a question. But the problem with this chart is, you know, so we had things like, okay, this was like a no, right? If you had too many vectors, it couldn't be Li. Therefore, it couldn't be both. And this was a maybe, and this is a maybe, like all that kind of thing. The problem with this is, I can fill this all out, let you guys remember how that goes. You have to know the dimension of your vector space to be able to use this chart. Yeah, this is a lot of people today.
I was going to say this today.
Yeah. So, but if we were working with one of these vector spaces, we would know what its dimension is, and we could just compare that with K and figure out where we're at in this chart. But we don't know the dimension of this vector space at all. We don't know it. The only thing I can guarantee you about the dimension of this vector space is that it is at most 4. can't be more than that because after all, these polynomials are living in P3 of R, which is 4-dimensional. So it's at most a 4-dimensional vector space. It could be smaller and it just doesn't look like it, right? So what would you recommend? Does anybody want to suggest what I might want to do here to kind of work on solving this?
First off, figure out how many, what K is, but just counting how many vectors. In.
Sure, we can kind of keep track of them this way. We have V1, V2, V3, and V4. So there's 4 vectors here. So we do know what K is equal to in terms of counting. There's 4 vectors there. But what would you recommend that I do if I want to find a basis for this thing? Yeah, Jose?
Just see if it's LX.
Yeah, we need to know whether these vectors are Li or not. And to do that, we need to set up a matrix. That's the answer to like every question in this class. Put it in a matrix. How do we put these vectors into our matrix?
Columns.
Columns, exactly. So for my solution, right, I'm going to build columns of a matrix here. And just to keep in mind that you're not literally putting the polynomial itself into the columns, just the coefficients. So like there's a constant term here, and then the 1 doesn't have any x's or x squareds or x cubes on it, right? And then the next one is 4 plus x, so that's 4 plus 1x, so we could just write it like that. And then the third one is 4 plus x cubed, which we could put into the matrix like this. I don't want to see any matrix tomorrow where there's x's inside the matrix. These are just numbers that go in here, right? And then the last polynomial, ooh, I threw a little curveball here. I wouldn't probably do this, but I put the constant term at the end. So I've got to go backwards now. 5, and then -2, and then 0, and then 2. Maybe looking like that. Okay. And so we're going to test whether these are Li. Why aren't we testing if they're going to be a spanning set?
It's given. It's already a given.
It is already a spanning set. Thank you. Because V is the span of those vectors. Now, when I say it's a spanning set, I mean it's a spanning set for V. It might not be a spanning set for P3 of R, but remember, P3 of R is not the vector space right now. The vector space is right here, whatever this is. And so these vectors will span whatever they span. And that is what V has been created to be, the span of those vectors. So they are a spanning set. It's really just a question of whether they're linearly independent or not. Let's just remind you guys when I say basis, right? When I say basis, that's just 2 things. It's Li and spans V. Those are the two conditions, and we've seen that over and over again. Well, so this is my matrix. As always, we need to do elementary row operations and try to get this thing reduced. I've already got a couple of pivots like that. I actually have an entire row of zeros here. People get really excited about rows of zeros, I notice. There actually is not the point. Okay, don't get too crazy. The reason there's a row of zeros here is just because there's no x squared terms appearing in any of these polynomials. So it ends up corresponding to a row of zeros. But essentially, this will be a pivot right here as well. Technically, I should permute those 2 around. I'm not going to be too fussy with you guys about that tomorrow. I will be much less fussy than I was on the first exam about like the details of the EROs. If you just want to circle where your pivot positions are and then draw your conclusions, that's going to be good enough for this. And if you happen to make a mistake and you get it wrong in terms of the row echelon form, but you answer the question based on whatever your row echelon form is, and you answer it correctly based on that, I will give you credit for that. I will give you the vast majority of the credit on the problem because that's really what the question is about. It's not so much about doing the EROs. So based on this, what would you guys tell me? Are they Li? No, there's a free variable right here, right? This last column has no pivot in it. It's a free variable. So what would I do if I want to get the basis then?
Get rid of that now.
Get rid of
The third one. Or the, sorry.
the fourth
Fourth row.
column. Yeah, the fourth column. I would get rid of this column. Yeah. And that would really just mean I'm erasing this vector from my set, and the remaining vectors are Li, and they are still a spanning set for V. So that's the answer. That's the answer. So you just have to throw away a vector, and you end up getting the answer for it. Okay. Everybody following along on that okay? So this is actually only a three-dimensional vector space. If I had known that ahead of time, if I had known that this was three-dimensional ahead of time and I saw that k was equal to 4, I would have crossed off Li hours ago, right? Because I would have said, wait a minute, if k is bigger than the dimension of V, then it's definitely not Li. Yeah.
Couldn't we have seen what the dimension would be based on the x cubed? We just take that, put sub that for n, add 1 to it, and see that the dimension is 4.
That would have been if V was the entire P3 of R. What is this vector space, guys? This is the span of a handful of vectors that I have grabbed. In other words, it's all possible linear combinations of these 4 vectors. That is, by definition, what the span is. So we don't really have a good idea of exactly what V is. If somebody said, well, if somebody asked me, what is V? All I would be able to answer is, oh, it's all possible linear combinations of 1, 4 plus x, 4 plus x cubed, and 2x cubed minus 2x plus 5. That's all I could say. There would be no concise, easy way to say what V is other than just reading it out. Yeah.
So in this case, if V was S, then we would have known V would have been P3 of R, right?
If V was S, there is no S here, so I'm a little mixed up.
Like, just in general, like if you give us, find a basis for S is equal to the span of that, would we assume that V would be equal to P3 of R?
If I call this S, then all I'm doing is changing the name of this thing. I'm not substantively changing what I have to do here to solve this problem. That would literally just be renaming the space. So it wouldn't be anything that would change my approach here. Yeah. I mean, I know when I write S, it sounds like it's a subspace. But as a subspace, it could be equal to the whole P3 of R or not. I don't really know ahead of time. Yeah. Let's say that once we decided, great question. So what she's asking me is, why did I not go further and like introduce the free variables and like actually solve this system, right? I would have done that if the question asked me to write down the linear dependency. So these 4 vectors are LD based on this free variable, right? Actually, you know, this is a good, we might as well follow up with this. I like that you brought that up because this is something else that we need to be able to do, which is how do we show that these vectors are actually LD other than just saying, oh, there's a free variable here. So what you could do is you could say, all right, I have constants C1, C2, C3, and C4 aligning up with those columns. C4 is free. And so you know how I usually like to just call that T. Okay, and then I have to just solve this system by back substitution. So like this bottom row here, if I just read it off, kind of erased it a little too hard here. That's a 2, I think. So this is just, the bottom row is just the equation C3 plus 2C4 equals 0. Right. And so if I solve that now for C3, I get negative 2T. Now, what everybody needs to realize is that this is just kind of a tedious calculation that I could have asked this question. This part of the problem is really just a Gaussian elimination thing. It really goes back to chapter 2, goes way back to September when we were doing this stuff. So this equation here is just C2 minus 2C4 equals 0. Again, I kind of erased this a little harder than I should have. This is a 5 and a negative 2 here. This middle row doesn't tell me anything, by the way. Rows of zeros, they never tell me anything useful. I can just like pretend they're not even there. But this second row allows me to solve for C2. So C2, if I solve for it, would be equal to 2 times C4. So it'd be 2T. All right, and then, oh boy, the first one's gonna be the end of me. The first equation is a bit messy. C1, I'm gonna come over here. C1 plus 4C2 plus 4C3 plus 5C4 equals 0. That's the first equation. You do have to write that out. Okay, and now if I isolate C1 by moving everything to the other side of the equal sign, I can solve for C1. So if I move things over, I'll have -4 times C2, which was 2T. I'm plugging in the values I already have. And then -4 times C3, which was -2T. And then -5 times C4, which was T. Okay, and if I clean this up, it looks like it's -8T plus 8T minus 5T. That would actually just reduce to -5T. So we would have C1 equals -5T. With me? And then to create the actual linear dependency, what would I need to do now? You remember how we actually create this equation that gets these 4 polynomials to cancel out? So there's this linear combination equation. That is what we're ultimately trying to write down. How do we get to it though? What do we have to do with this? I'm sorry? You know, that is what we often do. But in this case, we actually are doing something slightly different. I'll come back to that bust out the T idea in a second and explain where that comes from. You remember what it is?
Write them in the, right, you say T is like all real numbers.
We actually don't want to choose T to be all real numbers. We want to do. Yes. Are you looking at something there? Right off my notes. Yes. Yes, guys, you need to choose a specific number for T. Remember that? Good thing we're reviewing it. Okay. This is very likely I might ask this. This is a very natural question. Plug in a value for T and that allows you to actually get numbers here. That gives you these numbers. And now I can write down my linear dependency. The linear dependency is C1 times V1 plus C2 times V2 plus C3 times V3 plus C4 times V4 canceling out to 0. So remember that linear dependencies occur when you can plug non-zero numbers in for those constants. And right now I have some non-zero numbers that I can use. So -5 times the first polynomial, right? And then +2 times the second polynomial, plus -2 times the third polynomial, which is 4 plus x cubed, and then +1 times the last polynomial, which was 2x cubed minus 2x plus 5. Unless I've made a mistake, this should all cancel out to 0 if I did the math right. It actually doesn't look like it cancels out to 0 to me. Oh, yeah. Did I mess it up? I'm sorry?
On C3.
C1 is -1, C2 is 2.
That's not.
Pardon? That's right, isn't it?
No,
Yeah.
yeah.
C3 is -2, and C4 is 1. So what did I do wrong? I can't believe it. The matrix is good, right? 5 minus 2x, 0x squared, 2x cubed. That all looks great. It's already in row echelon form.
That's right. That's right. Okay.
Does that all cancel out?
-5, 8.
Oh, you know
2x.
what I'm doing? Oh, I know why I'm screwed. I know why I'm screwed up. It's because on all of these 3, I started with the constant term. And then for some dumb reason, I put the cubed term in the front of this one. If I rewrote this, yeah, it is actually correct. This is just, I should write this as 5 minus 2x plus x cubed. Sorry, guys. I'm here to also demonstrate what you shouldn't do tomorrow. Don't confuse yourself. Even the professor's now confused by writing the polynomials in different orders of terms, right? This should now work. If I actually work out that equation, it should cancel out to 0. So this is my linear dependency. Catherine, is that what you were kind of getting at? Great. It's a great question. I'm glad you asked that. I didn't really review that in the other review either, so.
Were you missing the 2x cubed, Dr.? 2x cubed on the very
On
top?
this one?
Yeah, because then
Yes, yes, I am. Oh my gosh. 2x cubed. Yeah, that should have been 2x cubed. Tristan?
So what kind of question would you be asking that would require us to do this? Like, would you ask just what is the linear dependency?
Yeah, I might say something like, here's a bunch of vectors. Are they Li or LD? If they're LD, write down the linear dependency. Yeah, that's right. Now, if the vectors are Li, I won't be asking you to write down a linear dependency because there is none to write down. But yeah, I could just ask you, give me the linear dependency. Yeah, good question.
Would this be the only one that dependencies, because technically you can choose the third, so B3 could be B4 and B3.
Oh, if you had put these in a different order, in other words, yeah, you could come up with other equations based on sort of setting up your matrix differently. So your free variable might be associated with not the fourth vector, but the third vector, for example. That's totally possible. Yeah, exactly. So yeah, you can get more than one correct linear dependency. The other thing you can do is the person next to you might have chosen t equal to 100. And that's also correct. They would just have they would have this thing multiplied through by 100. And that's also right. Everybody would be right in that scenario. Kind of make sense? Okay, super guys. Good, good, good. Let me give you another problem. I'm kind of, yeah, I want to do this one. Go to number 2. Oh, I have one other comment, but I see 2 hands up first. Jose?
one other question.
Yeah.
When you want us to write for the basis, would you want us to write basis for V and then the set of those 3?
If I ask you for the basis, yes, actually, thank you for that. I want to actually write down the basis. The basis would be equal to the set of 1, 4 plus x, and 4 plus x cubed. And you would list these vectors with commas between them and using a set notation. That's actually very important as well. Yes. Did you have your hand up too?
Yeah, let t equal 0.
That is the only value of t that you cannot use. If you let t equal to 0, the whole equation just kind of collapses and you don't actually have an interesting linear combination of the vectors at all. So when you're choosing this t value here, you can choose any value of t except for 0. And also, you could have had more than one free variable. This one only had one unpivoted column. You could have had more than one, in which case you would have had, let's say, r and t. And if you came over here and you had r and t, you would have to choose values for both of those variables. And as long as you don't choose them both to be 0, you'll be fine. You'll have a valid linear dependency.
If they both be 1.
Yes, they could both be anything else other than 0 and 0. Yeah, that's a great point. I have another comment because somebody, when I first wrote down these constants, somebody was asking me about busting out the variables on this, which we so often do. And yet somehow that wasn't the thing we wanted to do here. Here we actually wanted to plug in a number for t. So the question is like, what's this busting out the variables going to do for me? Well, if I actually come back to this matrix again, have we seen any other scenario where we've had a matrix and we've augmented it with a column of zeros and tried to solve the system? And if so, what was that called? Does anybody remember that? The null space of a matrix. And sometimes people get confused because right now this problem has no matrix reference at all in the question. And yet somehow we end up solving this problem by essentially setting up a matrix augmenting it with zeros, which is the same thing that you do if I give you a matrix and I ask you to find the null space of it. Now, if I asked, let's just back up for a second. If I had asked you to find the null space of this matrix, what would have been different about the work we did? Well, we would have augmented it with zeros. We would have done the EROs. We would have set up the free variables. We would have solved it by back substitution. And we would have come up with these expressions right here. But if I was looking for what the null space of the matrix was, I would not plug in t equals 1. Instead, what I would do is I would make my answer would just be the set of, and I'd just write it down, negative 5t, comma, 2t, comma, negative 2t, comma, t, such that t is a real number. And if I wanted a basis for that null space, I would bust out that t right now. And in that case, I would have exactly what Marco was saying, which is negative 5, comma, 2, comma, negative 2, comma, 1. And that would be a totally different problem. Although the work was largely the same, it would be answering a totally different question. I only bring that up just because sometimes people get mixed up, like, wait a minute, am I doing a null space of a matrix, or am I finding a basis for a subspace? Like, they can have some similarities. And it can be a little bit easy to get them kind of confused. Everybody making sense of that? Seem okay? Okay, super. By the way, can somebody tell me before I go to number 2? This is just a side thought, question. I don't know what to call this. This would not be something I'd put on the test, but I see so many people getting a little bit queasy about this. What's the difference? I mean, people should understand this. This is important. What's the difference between, let's just say, the set of V1, V2, V3, and the span of the set of V1, V2, V3? For once and for all, I want to like set the record straight about like, you know, because sometimes I'll see people write answers and they'll have the word span in front of their answer, and then other times they won't. And I sometimes not sure if people really know whether they're supposed to have that word there or not. And so this is a good thing to kind of ponder for a second. Question?
I was
Or comment?
I was gonna try to answer the question.
Oh, I would love that. I can take a break.
So the span of V1, V2, V3 is within the one with curly braces above, like it's.
Yeah. Well, keep going.
Well, I don't know, that's kind of it.
Wouldn't it be a span would be
Hey guys, smile.
form a linear combination of
What's that?
span would be all the vectors that can form a linear combination.
Yes,
of the
it's
subspace.
all possible linear combinations of these vectors. If I ask you for a spanning set, it's just this. It's just this list of vectors. But what do they span? They span this. This thing down here, guys, is not 3 vectors. It is infinitely many vectors. This thing down here on the second line is all possible linear combinations of these 3 vectors. And it's actually a subspace of whatever big universe you're working in, if that makes sense. So sometimes if I ask you for a spanning set, you should not write the word span in front of it. Or if I ask you for a basis, you should not have the word span in front of that. Now, the truth be told, I never take off points for that. If you accidentally had that there, it's not something I make a big deal over, but it's just good to know that that actually is correct. I gotta see, why is this thing? 1 second. I've lost my video somehow. What did I just hit the stop video button. Okay. Should I write something down about that? Marco?
The basis, the same as like the spanning set.
A basis is a linearly independent spanning set. It's this right, yeah, exactly. So this is just a set of vectors. Whereas this is an entire subspace. And guys, these are not the same thing. This handful of vectors here is not going to be a subspace. I can guarantee it. Because you have to take all possible linear combinations of those vectors in order for it to be closed under addition and scalar multiplication, yeah? So this is just a dead set of vectors. It could be a basis or a spanning set for whatever they span, and that's the subspace. That's where the real, subspace is occurring from. Okay. Ready for another one? Okay. Do you guys remember, we learned what a subspace is. And to check it, the first thing we learned was it has to be closed under addition and scalar multiplication. And then later we learned that, oh, but wait, if we can express our set as a span, anytime you take the span of anything, it's always a subspace, right? So some people have kind of got this idea that, oh, I'm not going to ever check closure under addition and scalar multiplication again. Because after all I have to do is take my subspace and find my spanning set and express S as a span of that, right? And a lot of times you can do that. Do you remember the problem about the 4 entries of a matrix adding up to 0? Right? I mean, these are matrices that look like this. To show that these matrices formed a subspace, all you had to do was bust out the variables and write this thing as span of the 3 matrices that correspond to those 3 variables. So that works great most of the time. But there are some examples where I can create problems that will force you to check the closure under addition and scalar multiplication because you just can't write down the form of the vectors. And that's what I want to show you here. So here is an example. Suppose that T going from V to W is a linear transformation. This is another topic we need to talk about, I think, right? A linear transformation. And I'm going to let S be equal to the set of V in capital V. This is another one that I did not do on the last review session. So this is a new problem. T of V is equal to the 0 vector of W. Okay, this I don't have a single colored marker. I can probably get by with this. So I'm gonna draw you guys a quick little picture if I can. I don't draw very many pictures at 250V, but I should draw more. I have one universe V, which I just draw as a big circle. And I have another universe W, which I also just draw as a circle. And my T is just a function. And you've probably seen this before in your basic math classes that you can kind of draw, you can view your function as like arrows with inputs on this side and outputs on this side. Okay, so we're talking about linear transformation with 2 vector spaces V and W. But somewhere in both of these vector spaces, there has to be a 0 vector. And I like to draw it just down here at the bottom. And of course, we proved in class yesterday that a linear transformation must respect the 0 vector. So in other words, T of 0 has to equal 0. Do you remember that from class just yesterday? But there could be other vectors that are also being transformed to the 0 vector, right? And maybe there's vectors up here that are just going any old which way. I don't really know. Okay, but there might be, a fair number of vectors that are getting sent to 0 by this transformation. And I'm going to just, again, if I had a colored marker, I'd shade this into a color. Well, I guess I'll just do a thick shading here. This right here is what S is in my problem. It's those vectors in V that get transformed to 0. And then here's the problem. I still haven't stated the question. The claim is that S is a subspace, show that S is a subspace of V. Yeah, by the way, any of you who have ever seen any of this before will maybe recognize this is something called the kernel of a linear transformation. We're gonna get into that a whole lot more next week. But for right now, it's a perfectly great question to review some of this chapter 4 stuff. So you really cannot solve this problem by just figuring out how to write S as a span. You can't do that because after all, I didn't really give you much information about T. I just said it's some linear transformation. So that has already made this into kind of more of a theoretical problem. It's a little more theoretical. I don't actually know what the formula for T is. Yesterday in class, we did tons of examples of linear transformations, and I always gave you the formula. Here, I didn't do that. I just said, suppose it's a linear transformation, and now I want to show that this is a subspace. So since I don't have a formula or anything to really crunch a calculation out of, I have to do this one by the old method of just showing that S is closed under addition and scalar multiplication. So I think I need more room, so I'll do this over here. Let's see if I can check this. So when you're writing these up, guys, be sure you try to help me find your work. Separate out there's always two parts to this, right? We have to check the closure under addition and then the closure under scalar multiplication. Back over here again. All right. Everybody so far so good? So closure under addition, the write-up is so important on this, right? We have to grab two vectors that are in S to begin with and add them together and try to convince ourselves that the result is still in S, right? So let's let V1, comma, V2 be elements of S. Eventually, I'm going to add them together because this is closure under addition. But I'm not going to add them together right yet. I have one other thing I want to do first. Does anybody know what I might want to write down first before I start adding the vectors together?
Define sort of arbitrary variable for each.
Well, that's what these are. These are the notations I'm using. Now, you could call these V1 and V2, or you could call them X and Y, or you could call them A and B. I don't really care the actual notation you use. It's kind of up to you. But I want to know, what does it mean that these vectors are in S? It means that they're in this shaded bubble here, right? Which means that what happens when I hit them with T, they go to 0, right? So this would just mean, let's write it down actually that way. This means that T of V1 is equal to 0 and T of V2 is also equal to 0. Closure under addition. I take two vectors in the set. I'm going to write down what it means that they are in the set. And eventually I want to add these vectors together. Now, of course, when I add them together, what I get is V1 plus V2. But the question is that still in S? Because that's what closure under addition means, yeah? Now, to be still in S would be that if you transformed V1 plus V2, you should still get 0. Exactly. Let's check if that happens. Let's check that. So let's take a look. If I transform V1 plus V2. Now here would be, so what we want, okay, don't write this down yet. We want this to be 0, right? But this would get my red pen going because I'm like, wait a minute, they've jumped right to the thing they're basically jumping to the answer before they actually show how to get there. So that equals 0 is great, but it needs to be like way over here, right? We need to like fill in what comes into the middle first. And what are you going to do with T of V1 plus V2? And I can split that up because why?
Because
Can I write it like this, guys? We sure have seen that a lot. And why is that? What is that property called? T respects addition, right? So, and that's because T is linear. So we're assuming here, suppose that T is linear, so that means that I have to be able to split it apart like that. So this is just since T respects addition. I probably wouldn't expect you to necessarily write that down, but it never hurts. It never hurts, right? Okay, so now you got T of E1 plus T of E2. What is T of E1? 0. What is T of E2? 0. And so what you have is 0 plus 0, and sure enough, that does equal 0. Aha! So this means, I'm going to go ahead and draw my conclusion now. This means that V1 plus V2 got transformed to 0, and that means that it is in S, right? That's what S was defined as. It's those vectors from V that got transformed to 0. So what we're saying is if we start with two vectors that are in this shaded bubble here, and we add them together, the result stays in that shaded bubble. And that's closure under addition. Exactly what that means. Good enough? Kind of make sense? Let's try the scalar multiplication. Okay. For this one, what do we need to do? We need to have a vector and a scalar this time. I usually like to use K for my scalar. So let K be a real number. And I have to grab one vector. I'm just going to say V1 be as above. You've seen me kind of use that, the rubber stamp statement to start off my proofs here. So V1 is just the same V1 that we had before. And I'm going to take a single scalar this time. And then what I have to do, guys, is look at K times V1. Do the scalar multiplication. My question is just going to be, is that still in S, right? So to check whether it's in S, right? So I'm going to take K times V1 to check if that's in S. I have to transform it and see if I get 0. Right? So what's your knee-jerk reaction when you see something like that? T of K times V1, what are you going to do? That K comes out, and that's, again, because T respects scalar multiplication, right? So T, I'll just say since T respects the scalar multiplication, that's going to be the reason for that one. Yeah, great. So this just becomes K times 0. 0 vector of W, actually. And this is, it is equal to 0. Actually, you want to know the honest truth of the matter? Technically, you have to prove that. I mean, you would have to prove that. I mean, I don't think that was not one of our axioms, was it? Was there ever an axiom that said if you take your 0 vector and you multiply it by any scalar, it's still the 0 vector? I don't think that was. So, don't worry about it. I didn't go over it. I wouldn't ask you that. This would be in Math 307. I would not even hesitate. That's an easy question. Ask people to actually show that. If you're interested in it, I'll show it to you later. But we can just kind of assume that this follows the normal arithmetic that we're used to. And so because we get 0 here, then K times V1 is in S, and we can check that one off. Absolutely. So guys, we have a subspace. Does that make sense? Any comments or questions on this one? Should I make like a specific example of this? Maybe I should. Maybe I should make a specific example. Now I'm going to be winging it though, if that's okay. I didn't really pre-prepare one. What I mean by a specific example is I should actually write down a specific transformation and see if we're good with it. So let's do this. Let's define, so I'll call this number 3. Let's define T to go from P2 of R over to P2 of R via, and then here's my formula, guys. I'm gonna take my polynomial P of X, and I'm winging this. If the numbers come out messy, don't blame me. Let's do P prime of X plus 5 times P of X. Okay, I'm making up a problem. And this is it. And what I would like to do is 2 parts. Part A is going to be show that T is linear. I'm going to try to show that this is a linear transformation. That's something else we need to practice before tomorrow. And then we'll follow up with a part B, which is now that this is a subspace, it has a basis. And I can ask you to find it. Find a basis for S as defined in number 2. So I'm really getting away from my handout of problems. I was going to just repeat the problems from Sunday, but I'm sort of starting to get excited about new problems. So we're just gonna do this one now. Okay, actually, I'm gonna come back over here. So let's start by checking that T is linear, because that's a good thing to review. What do we have to do to prove that T is linear?
Respects addition.
T has to respect addition and scalar multiplication, both of the 2 operations. Okay, so let's try that. Let's see how that part goes. So let's get to part A here and see if we can solve this one. So T respects addition. I got to start off with that. So this means that I need to plug in like 2 polynomials. I've got P of X, maybe I want to take Q of X and like add those together, right? So I could say something like this, right? P of X plus Q of X. That would be a reasonable notation, right? For my 2 inputs, because I'm doing an example involving polynomials. And what I have to do with this, guys, is first of all, let's not forget, we're going to leave white space underneath this transformation for sure, right? Leave that as white space. I'm going to take this input and I'm just going to substitute it right where I have my formula here. So where I have the P of X, now I'm going to write it as P of X plus Q of X. So what do I have to do on the other side? I have to take the derivative. So this is P of X plus Q of X prime, and then plus 5 times whatever's in the position of P of X, which is P of X plus Q of X. So try not to jump too fast to just what the answer is. You already know that you're hopefully at the bottom here. This is what you want to end up with. And if it helps you sort of as a guidepost as to where you're headed with this, to write this down, that's fine. But give yourself room to fill in all of the algebra in between here. Okay. Any suggestions or how I'm going to take this big mess up here at the top and work with it? So totally just expand it out, right? We actually talked about this in class this week, that you can split apart the derivative, right? And then we can also, of course, multiply the 5 through. So just break up all the terms into individual pieces like that. And that's good enough. What would you do next?
Regroup them with their like terms.
And what are the like terms here?
The P's with P's and Q's with Q's.
Good. Very good. Put all the P terms together. That's P prime of X plus 5P of X. And then I'll make some parentheses around the Q prime of X plus 5Q of X. Now, there might be some of you out there who are thinking, I could have gone from here straight to here in my head, and that I could have left this middle line off, and that would have been fine. I could see in my head to do that. Okay. I'm usually pretty lenient about this because there isn't there isn't a perfect rule for like what steps have to be shown and what you could combine together. But if I have to start scratching my head to figure out how did they go from there to there or something, that's generally not a good thing. So if in this case, if you had gone straight from here to here, I probably would have grumbled under my breath about it, but not done anything in terms of marking up your exam. I probably would have accepted that, but I probably would have been like, they should have shown one more step. Yeah.
We get partial credit for if, let's say, we have the correct start, have the correct end, but sort of not entirely get the steps in between, but get some of them.
Fumble your way through the middle of it.
Yeah,
I've seen that happen before. Absolutely. If you've got the framework of this set up right, I'm gonna be super stoked about that you understand that you're proving this, right? And that you've got the way it's supposed to be set up. I would totally be good with that. And I have seen that happen before, but it's not gonna happen tomorrow. You guys are all gonna get it exactly without any problems. This is just, we're really just talking about like personal preference, like how many steps do you need to show in the middle of this? So I would suggest you err on the side of, including extra steps. The thing is, as long as you're getting it right and it can be done in one's head, I'm probably gonna be okay with that. But the minute that there's a mistake, that's when showing your work is especially important, because if I can say, oh yeah, I know why they didn't get it right, it's because they made they miscopied a number, right? As opposed to if you don't write anything down and it's just wrong, then I can't help you. So just a quick little sidebar about exam strategy, write all your stuff down, right? Don't erase it. I hate seeing the erasers come out. If anything, use a pencil and cross it off and go to another scratch paper. Right, because if there's no work showing and it's wrong, then my hands are tied. I'm like, how do I give this person? I would like to give points, but I can't if there's nothing there to form a foundation of the answer. So yeah, so including this step would probably be good, right? But if you left that off and went straight from here to here, I'd probably be okay with that as long as it's correct at that point, okay? So this is it. This is showing that T respects addition. Is that clear to everyone? Does that look okay? Let's take a look at the scalar multiplication. And that's the second part, right? Now how does that one shake out? So we start off with T. This time, if you remember, we have to have our K again, right? And this is just K times whatever our P of X is. Yeah, exactly. So you just grab your P of X and scalar multiply it by K. I'm gonna plug this. Now see, again, the temptation is you already know that you want the K to be factored out. But resist the temptation to just put that down on your paper immediately. That's actually supposed to be at the end of this whole thing, right? Way down here is where it ultimately will hopefully be factored out. Don't factor it out in the first step, or I'm gonna be like, wait a minute, they just stole the whole thunder of the problem, right? So we wanna actually derive this thing. So let's just take this whole thing and use the formula in the box on it, this formula right here, okay? So I have to take the derivative of this thing, K times P of X prime, plus 5 times K times P of X, yeah? Gonna look like that. And what is this sort of begging us to do? Factor out the K, right? When you take derivatives, constants can come out, right? So yeah, this is just K times P prime of X plus 5K P of X. Sorry, I'm a little bit scrambling for space here, but I'm gonna stick the K in there and factor out the K, and that leaves me with P prime of X plus 5 times P of X in the brackets there. Is that legible for everyone? Reasonable? Again, this is maybe an even more obvious example of a place where you might say, wait a minute, I could easily just go from here down to here. And yeah, you're right. If you did that and you didn't show that middle step, I wouldn't even bother you about it. I would totally be okay with that. What I just don't want to see is somebody writing this down first and then writing this down next. Because this is the end of the line, not the beginning of the line. Yeah. Okay, so guys, T respects addition and scalar multiplication, which means that it is a linear transformation. So that's part A. That's part A, show that T is linear. Okay, the next thing is part B, asks us to find a basis for S. This is gonna be the more interesting part, I think, in some ways. So let's take a look at part B. So S is those inputs that got transformed to 0. So in other words, you're sort of going to do this. You're going to take your input, we don't know, let's just call it P of X, and you're going to set that, you're going to transform it, and you're going to set it equal to 0. This is what we want to work on. The question is, which polynomials will get transformed to 0, right? T of V equal to 0. So really we're solving here, guys. What we're doing is we're solving for P of X. Now, if I write out what my transformation is, let me just do that. This is really P prime of X plus 5 P of X. And again, this has been set equal to 0 like so. It has been set equal to 0 like that. And the goal here is to solve this for P of X. I think I'm gonna use some space over here. Actually looks like we have to solve a differential equation right now. You know, we're basically trying to solve what function has a derivative that is equal to the negative of 5 times itself. It's basically a differential equation. It's actually a first order linear differential equation. So we could pull out our integrating factors and do all that jazz. But actually, we're not going to do that. I'm not going to ask you guys questions about chapter 1 tomorrow. Don't worry. That'll come later. For right now, yeah, I need to solve this for P of X, but why is it something we can do pretty easily without going back to chapter 1? The reason is that this P of X isn't just any old function. It's actually living in this universe. So I can actually write it in the form of a quadratic polynomial. And that's actually what we need to do right now. So I'm going to actually write this guy. I'm going to write this P of X as ax squared plus bx plus c. It's some quadratic polynomial. Okay, and I bet I can take the derivative of that and add 5 times that and set it equal to 0. Let's just try it. So the derivative of this, right, p prime of x, that would just be 2ax plus b. And if I now kind of put it all together, what is p prime of x plus 5 times p prime of x? That's sorry, p prime of x plus 5 times p of x. Well, we can just copy it down. 2ax plus b plus 5. Let's just throw the 5. Let's distribute the 5 into all of the terms. So 5ax squared plus 5bx plus 5c. And this is equal to 0. I just want to be clear what we're actually trying to do, guys, is we're trying to solve for A, B, and C. We're trying to figure out which P of X's get sent to 0, right? So that means I'm solving for the coefficients, the A, the B, and the C. I don't want to see anybody solving for X. Okay, the X is actually not an unknown here. The X is actually part of the polynomial. So we're not like trying to like use the quadratic formula or anything like that. There's nothing to do with that. This is literally just solving for A, B, and C. And what I'm going to do with this is something you've seen me do before. I'm going to reorganize these terms with the x squared part together, and then the x part together, and then the constant term, right? I'm just gonna do each of those. So the x squared term, I'm gonna put it in the front here, guys, 5ax squared, right? And then the x term would be 2a here and 5b here. Right, times x, and then the constant term is b plus 5c. Oh, man. This is not going to be very interesting. I was winging this problem. I knew this is why you don't wing stuff. When I put 0 over here, that 0 is actually the 0 vector. It's not the 0 number. It's the 0 vector from W. So this 0 is literally 0x squared plus 0x plus 0. You should think of it that way. That's really what that 0 vector is. And see, now guys, this is why this is kind of turning out a little bit lame. This x squared coefficient has to match with that. This one has to match with that. And this one has to match with that. Okay. And what you might notice is, well, that tells me that 5a has to be 0. And then 2a plus 5b has to be 0. And then b plus 5c has to be 0. All of these coefficients here, right, on the left side, they have to all cancel to 0. And I was hoping we would get something more interesting. But by now, you guys have probably already solved this in your head. Which is that a is 0, and therefore from the second equation, b is 0, and therefore from the third equation, c is 0. So the unfortunate, I mean, it is what it is. The conclusion here is that a, b, and c have to all be 0. And that tells you that which polynomials actually get sent to 0, only p of x equals 0. Because a is 0, b is 0, and c is 0. If you go back to your polynomial and you plug these numbers in to figure out what is p of x, well, this just means, sorry, I'm going to go from right to left here. This just means that p of x is 0. And so there's nothing really wrong with that. It just means that your s is trivial. So s is just the 0 vector only. It is just that one trivial vector. And so actually, that subspace, it is a subspace, by the way. Nothing could possibly be more closed under addition. 0 plus 0 is 0, and any scalar times 0 is 0. It is definitely a subspace, but it is a trivial subspace, and it has no basis. So if you have something, it's basically 0 dimensional. And so it has no basis at all. You can't even talk about a basis for this thing. So I didn't make a very good example. We're going to be doing this a lot more actually later in chapter 6. We're going to come back to this idea. So I will just leave it at that for now. But it's good to practice it now. Practicing that a transformation is linear is for sure a good thing to do. And then yeah, finding a basis for something. It's just this turned out to be kind of trivial. Okay, so far so good? Sweet. I've got another problem I want to ask you. Let's change gears a little bit. Let's go to number 4. This next one I'm going to do, I like it so well that I did it on a Sunday. So if you were here on Sunday, you will recognize it. I'm going to do it again. And if you're here on Sunday, don't tell the answer because you already know the answer. Some of you are already ahead of the game here. So this is number 4. And what it says is, suppose A is equal to an M by N matrix. And let's assume that the row space of A is equal to the null space of A. And here's the problem. I want you to prove that n is even. I want to prove that n is even here. See if I can do that. Prove that n is even. It's kind of weird. It's a very basic little question. So it's obviously pretty abstract. We don't have a specific matrix here. Just remember with me, if you will, for a second, the row space though of a matrix is always a subspace of, do you remember which one? Rn. And the null space is always a subspace of Rn also. So that's right. These are both subspaces of Rn. Now, if I talk about the column space, that's a subspace of Rm, right? So that recap handout thing I passed out, it's in Canvas, and it's also been written down all over my board outside my office. That's a good chart to pretty much have memorized if you can. So what are these things subspaces of? These two are both subspaces of Rn, and I'm assuming that they happen to be the same. And why would that mean that n has to be even? I wonder. I have to think about this for a minute. Does anybody who wasn't here on Sunday want to suggest maybe what the key relevant result is, or the key thing that we've talked about is that would help us to do this? It's a big deal. Talked a lot about this one. And you might not even be right, but you know, the idea is without it, you don't have to see the whole solution to the problem to be able to just at least write something down. Super. The rank nullity theorem is what comes into my head because I see the n, which is part of the rank nullity theorem. And the rank nullity theorem is when you're dealing with a matrix and you're talking about pivots and non-pivots, right? And the row space and null space and column space are all kind of tied into that conversation. We learned all of that kind of in one lecture, yeah? So if you think that this problem has something to do with the rank nullity theorem, but you don't know how to solve the problem yet, what you should do, to all the test takers out there that want to maximize their credit on this exam, you at least write down the rank nullity theorem. Even if you're not sure it's going to help you, write it down. Okay, so this is a theorem that is easy to write down, the rank nullity theorem. And if you write it down, and if it's relevant, I'm going to give you points for that, even if you don't finish the problem. So let's write it down. The rank nullity theorem just says that the rank of A plus the nullity of A adds up to n. So that's what we want to know. Okay. That look good to everybody? The easiest theorem in the world, right? You have n columns in your matrix. Each one is either pivoted, which adds to the rank, or unpivoted, which adds to the free variables, and the free variables give you dimension to your null space. The nullity of A is the dimension of the null space. Okay. Now I want this to be even. So how does this equation help me to see that it's going to be even? Marco.
Since the row space and null space are equal to each other, that means the rank of rows.
That's right. If two things are equal to each other, then their dimensions are equal. Yeah. So the dimension of the row space, that's also from my little chart. The dimension of the row space is the rank. Let's write it over here, actually. So let's just recall that the dimension of the row space of A is equal to the rank of A. Very good. And then also the dimension of the null space of A is equal to the nullity of A. Every single thing I'm writing down right now is increasing my partial credit as I go. As long as it's relevant. You start giving me the Graham-Schmidt process right now, probably I'm not gonna be too happy. But if it's something that's related to solving the problem, of course, I'm gonna give you credit for knowing those things. Okay, but these two spaces are equal, which means these two numbers are equal. So from the given assumptions, the rank of A is equal to the nullity of A for this particular assumption. Right? I'm assuming that the row space equals the null space, so the rank equals the nullity. That means that these two numbers are the same. It could be 5 plus 5, it could be 8 plus 8, it could be 25 plus 25. But the point is, when you add the same number to itself twice, it's going to end up being even, guaranteed, right? So we get 2 times the rank of A equals n. And so n is even. That's very true. N is definitely even in that case. N is going to be even for sure. Good enough? Okay, questions on that? This is a perfect level of like what I would expect, or what I might ask you. Something almost exactly on this level. It's really pretty short, and it involves big ideas. It involves big mainstream stuff that I've been flashing in your faces for quite a while. So I definitely think it's a good one to go over. Okay. Yeah, question. All I'm doing, yeah, good question. So all I'm doing is I'm saying that this nullity is the same as the rank.
Yeah.
So then I have rank plus rank, which is just 2 times the rank. Yeah. Yeah, I'm basically taking this left-hand side and I'm just replacing it now with this much. Yeah. Yeah, Marcus?
Instead of doing like all that by, like, after we explained that, since they're both in the same subspaces, that, they're equal to each other, we can just say that odd plus odd is even plus even is even.
If you wrote it out that way, yeah, that would be fine, because yeah, that's clearly covering both cases. Yeah, I would totally go for that. Okay, let's do some more practice, guys. That was number 4. Okay. Oh, do you mind if I make up another problem? I think instead of going back to this set of problems here, I was a little bit, well, I shouldn't say that. I think there was that one homework assignment that I sort of worked it all out for you guys. So there was a couple things from that I noticed, because it was on yesterday's group work, that people were having some trouble with. And by the time I got to my afternoon class, I sort of figured that out. But in the morning class, I didn't have that figured out. So I'm going to do another, I'm just going to make this one up on the fly as well. You're going to recognize this because it's very similar to something off of the group work that we did yesterday, but I'm going to make a new problem out of it. Let's just assume that the set of U, V, W, let's assume that this is an orthogonal set such that the norm of U is equal to 5, the norm of V is equal to 2, and the norm of W is equal to 3. And what I would like to do is show, oh, sorry. Didn't mean to wake you up. Show that the inner product of 3U plus V, sorry, let's just say instead of show, let's say compute. Compute the inner product of 3U plus V minus W with 2U plus 4W. So there was a example in the group work like this, and people were trying to just get the answer like without having to do anything, but actually this takes a fair bit of work. It's actually much more involved than it looks. So I'm talking about inner product spaces here, obviously. but I didn't give you an explicit inner product right now. You don't have a formula. So all you have is this particular set of values, and I ask you to compute this inner product. And guys, this inner product is a number. So when I ask something like this, at the bottom of your paper, I should see a number. Final answer should be some number, right? So does somebody want to, I know it's only been 24 hours since we did a similar one, but I just want to make sure we're all good on this. What would be the procedure here? Reed, do you have an idea?
What?
Yeah, you just use the axioms of the inner product that allows you to split this thing apart. Okay, so you can split this apart and you can already see you've got 3 terms here and you've got 2 terms here. When you sort of expand this all out, that's going to end up being 6 terms, right? There's going to actually be 6 terms there. So the first one is, 3u, so it's sort of the inner product of 3u with 2u, right? And then the next one would be 3u with 4w. And then we go to the next vector, which is v, the inner product of v with 2u, and then plus the inner product of v with 4w, and then minus the inner product of w with 2u, and then minus the inner product of w with 4w, like so. So let me write down the next step, and you guys tell me how you like this. So far, so good? So, by the way, this is coming from one of the inner product axioms. Make sure you know those axioms. I can write them down if we need to. But before I write them down, let me just finish this. So, would this be good? So, I'm going to take this and start working it out.
No.
Okay, good. I'm glad nobody's too happy with that, although you're all smiling. Yeah, this is actually what I see a lot. And the point here is, guys, it actually doesn't even make any sense. Because I don't know how to square a vector. What if these vectors were 2 by 3 matrices? You wouldn't take a 2 by 3 matrix and square it, would you? It wouldn't even make sense. Or multiplying vectors together. Right? When you're in a vector space, there's only 2 things you can do: addition and scalar multiplication. So if you see something like this, it looks like you're taking u times w, and that's absolutely not one of your operations. So let me erase this, okay? Nobody's going to do this tomorrow, right? There's always somebody who does this, but it won't be anybody in this room. That'll teach them to come to the review. Anyway, so what I need to do here is keep those inner product brackets going, right? So there's the 3 and the 2, I can pull those out, right? That's 6 times the inner product of u with itself. In other words, just be patient with this. I know it seems like I'm writing out so much stuff. You really do need to do that. It's the safest way to make sure you're going to get this right. So then we have a 12 that can come out, and then the next term we can pull out a 2. Remember, the constants can be pulled out of any slot. So I can combine them together and pull them out as I'm doing right now in all of these terms. So this is kind of long to write it out, but it is certainly the best policy for showing your work and also just to make sure you're comfortable with what you're saying. And now I've got them kind of lined up the way I want. Any suggestions on simplifying this thing at this point? Yes, Michelle?
We could cancel out some terms and make it 0.
Some of the terms can be canceled out to 0, exactly. And which terms are they and why?
From the 12 to the -2 term.
All of these, right? And why is that I can cancel those out?
0.
Right, so if I put something in the question, it's probably not just hanging out there for no reason. You're supposed to use that for sure. So the orthogonal vectors have an inner product of 0, right? So the inner product of u with w, that's gonna be 0, yeah? And the inner product of v with u, that's going to be 0. V with w is 0, w with u is 0. The only ones that wouldn't cancel out immediately, so I'll just say, because I'll just write the word orthogonal vectors next to this, so you can kind of remember why I canceled those out. The only terms that you actually have to really spend any time on are just the very first one and the very last one, right? Well, let's take a look. This first one here, can somebody rewrite the inner product of u with u for me?
It's the norm.
Is this the norm of u? Squared, thank you, right? So I just remind everybody really quickly, the norm of a vector, we've had this up many, many times. It's the square root of the inner product of a vector with itself. So if you don't have a square root on it, like here, there's no square root on this, that means you're squaring that norm, yeah? And then the last term, we have also a 4 times the norm of w squared, like so. So if we get this far, then we're just about home, right? We're just about home free with this. This is 6 times 5 squared minus 4 times 3 squared. That's 25 times 6, 150, and I subtract 36. What is that? 114? Yeah, 114. That would be the answer. Having the answer right is hardly anything that I care about. What I really care about is all the work, and have you really used the properties of inner products to come up with the answer. Anybody could miscalculate this. It's not gonna make a dime of a difference on the test, right? It's not really the big deal. Yeah.
So I understand that I gave their product, but I kind of missing the concept of like, what are these things and what do they intend, right?
Good point. So yeah, I know that this kind of went by quickly, this chapter 5. The idea here is that we are putting geometry onto our vector space. Because a vector space, as we discussed it in chapter 4, is totally about algebra, addition and scalar multiplication and a whole bunch of axioms. So this is an effort to try to create a geometric component to a vector space. And this inner product is modeled after the dot product that we use all the time in calculus, right? So anything you could imagine the dot product helping you to understand in calculus would be something that there would be an analog for here that would apply in any other vector space, not just for, you know, vectors that you can touch and feel and see. So for example, if I asked you, if I wanted to know the angle between these two vectors, keeping in mind that these might be two polynomials, or these might be two matrices, or these might be two calculus functions. They don't have to be things that you can actually draw. But if I asked you to find the angle between them in sort of the definition that we are using, we could do that. And you know, we had a formula for this, which is if you want to know the cosine of the angle between two vectors, you take the inner product of those two vectors and divide by the products of their norms. So you'd have things like this, and you can actually define the angle this way. So if I wanted to find the angle between this vector and this vector, then one of the things I would need to do in the numerator is I would have to find the inner product of the two vectors. And then in the denominator, I would actually have to find the norm of this, right? And the norm of this. I guess I could have asked for that too. I could have just, instead of saying to compute this, I could have just given you these two vectors and asked you to find the angle between them. That would have been a harder problem, because then you would have had to find the numerator and both of these norms. But you have all the information you need to be able to do that, right? And then calculate that fraction. Yeah. It's also supposed to show you the power of having orthogonal sets of vectors. I'll just give you, I don't want to turn this into a big philosophical we're trying to review for an exam here, but just so you know, if you're an engineer out